Hello and welcome to the video now, as my 3D printer is delaying me quite so with making the back armour casing upgrade video. I thought I would do an actuator update as it's been a while and I have been on with some new things with it. This being one of the older versions that I've shown in previous videos and this being the new version. Firstly though, I'll go over the parameters that I need to work in, as that kind of dictates the way I'm doing stuff and the order I'm doing stuff. So number one is materials and parts. So because I want to be able to make these actuators completely from scratch, essentially, by myself in the United Kingdom, I need to make sure that the parts I'm using are readily available, easy to get, and I'm basically not dependent on a random supplier at the other side of the globe. At least there needs to be multiple suppliers that I can get the parts from. This in particular is bearings, so I want to be able to just get bearings from a regular bearing shop. And the neodymium magnets for the rotor of the brushless motor. These need to be a relatively common size, so they're always going to be readily available. The second parameter is general machining and tooling. So a lot of these actuators have a lot of milled parts in them. That makes them very expensive and very, very expensive to do in a place like the United Kingdom, hence why a lot of them are made in China. But because I want to be able to make them at a decent price in the United Kingdom, I need to stick within machining parameters. Now, what I did in the previous video was I tried to utilize laser cutting steel to make gears and to make housings. This is still an option, but try to outsource these little small parts at an attractive price to get a laser cut, and actually getting a laser cut that actually wants to properly deal with you is quite difficult. So that is something I'm trying to keep to a minimum if possible. And the third parameter, which relates to the machining and to the parts, is the costs. The whole point of this is to produce these at a low cost for both my exoskeleton and any robots I want to make in the future and anything general, while ideally being able to put these on Patreon so that you at home can make these relatively easily as well. So if the machining and material costs are going to end up pushing this up to £300, £400, £500, maybe even higher per actuator, then that's not really any good. But so far I have been able to work within these parameters and get a result. For example, this actuator now costs I think about £60 to make. I'll try to put it on the screen. At least in materials, there is of course time on top of that. But making these for your own projects, you've kind of got to count that out. Now, as I don't want to disappoint the viewer, I will say now that I haven't got these actuators working properly yet. But as you'll see, I've narrowed down the design quite a lot. So while I was hoping to have it actually working in this video, I have also been thinking I've got quite a lot to cover on it, as I've tried many different stator designs and kind of gearbox designs, and I've also changed my idea on what to actually make this out of. So we'll go over to Fusion 360 and see how all this fits together. And here we have the 3D model of the latest actuator in CAD. So I've got the faceplate of the actuator that will basically bolt onto the exoskeleton itself. And I've now decided to have the bearing shim protrude out here, so the bearing can sit in that gap and then sit nicely onto the motor hub there. The idea currently, at least on this design, is just to have these 4 bolt holes that have bolts running all the way through the design to hold it all together, but they also double as the attachments for the exoskeleton. In the future that might change and I might have some dowels to hold this together separately. I think that's probably the best. But for ease of prototyping, this is what I'm going with at the minute. So if we take the faceplate off, you can see here we've got the planetary gearbox. So we've got the ring gear built into the casing and then 3 planetary gears running inside the ring gear. This currently gives a 6:1 gearbox ratio. I do want to experiment in the future with getting that down to 9:1. I think that'll be far better. But at the minute it's easy to print because the teeth are quite large at this size. This is currently mounted onto the carrier that doubles as the motor hub, but I have made this so, like with previous prototypes, the actual hub here can be made separately to the planetary gear holder. Removing the top of the carrier, you can then see the planetary gears and the sun gear in the middle, which is the drive input from the brushless motor. Rotating upside down, you can see the back plate with the hole in the center for the bearing to sit in, as well as this little holder for a Hall effect sensor, so that a diametric magnet can be mounted to the center here, so you can get a position. If we remove the back plate, you've then got the current rotor that I've printed out. This fits 36 magnets on the outside, which when we get to the stator, I'll go over why 36, but for now, we'll just remove that. And here you can see the other place for the bearing to go for the motor side of this. So you've got a good bearing at either side of the rotor. That is essential to keep it basically centered and square in the middle. And if I rotate it to here, you can see in this cutout here is where the stator actually sits. And how the 3D printed casing is basically the holder and aligner for the stator and the rotor itself. Now, while this version will be 3D printed mainly for ease, I have still designed it with the thought in mind that I can separate all of this down essentially into flat plates, CNC flat plates out of either carbon fibre or out of steel, and then build them up on the bolt holes and you'll get a perfectly well fitting actuator. Which, if we scroll on out, you can see how all of these individual pieces could essentially be separated out and machined as single layers. Now it's time to talk about stators. As for these stators, this is something I spent the most time on. If anything, one thing that I wanted to look into that I alluded to in a previous video was that I wanted to take a look at SMCs, which is soft magnetic composites. These come in a few different forms, but typically it is iron powder, silicon, all mixed together, bound together in something like an epoxy resin, and then cast into a shape of the stator. While these aren't particularly as good as silicon steel stators, what attracted me to trying this out was it's basically a lower tooling method of doing it. You don't really need much machining, and I knew I was going to have a problem with actually getting hold of silicon steel. So I did proceed to make some 3D printed molds, all with little pieces that could tap out separately so you never broke the stator itself. And I actually got pretty good at making these in the end. I made quite a few, this being one of the better ones. Another one here, and some bigger ones that I also experimented with. The issue with these, while they do work perfectly well as electromagnets, which I did test, I couldn't get these to work with regular ESCs, pretty sure because I couldn't get the correct back EMF signal. At this point, I decided to put the SMCs to one side to try get hold of some silicon steel plates to make a regular silicon steel stator, which brought forward the issues that I thought I was going to have, hence why I started with the SMCs at first. And that is that I could not find a British supplier of silicon steel, and that I basically had to go buy it off AliExpress in China. But I can't knock at the Chinese on this type of stuff because they cut them perfectly to size, 300 by 300 as on the advert, and they sent them, and I got the sheets in about 8 days. They even threw a couple of extra ones in, probably to keep me happy because they'll probably know that most of the cost of this was actually in the shipping being more than the actual steel. However, this did lead me on to another problem, which is why I'm trying to get out of using third parties for stuff. And that's that the laser cutter that I normally use, who I can't fault in general, couldn't get any silicon steel, and then when I wanted him to cut the silicon steel that I had, I didn't get a reply off him. Which, as a side note, something else that does annoy me in the UK, let me know if it's different in America, I imagine it probably is. But in the UK, once you're at the second week of December, you can't get anything done by anyone until the second week in January. It's the same thing every year. It does my head in. So again, there you just end up losing a month. Because by the time I actually got those silicon sheets, found them, got them, after admitting defeat on trying to find them in the UK, I was circa second week in December, so I kind of figured I'm not going to get anything done until January anyway. This was a point where I tried to perhaps push my own 3-axis CNC machine to cut these silicon steel plates. Now they are only 0.5mm thick. However, my 3-axis CNC is only really made for wood and maybe bits of aluminium. But I decided I need to try and give it a go. However, we'll go back into CAD and we'll take a look at some design decisions that I had to make to actually use my own CNC on this, and for efficiency on material. This is a 27 slot stator design that I've made and modified so I can use my 3-axis CNC. Now I'm going to do a separate video covering all of the different stators that I've tried to make, including the SMC ones. I'm going to a bit more detail on those, so I'll just be covering the ones that I've cut out of silicon steel. This one being the design that I started with and I kind of wish I'd carried on with. So I've made it so I can use a 3mm end mill. I didn't want to go any smaller than that. So all the radiuses are made for that 3mm end mill, including the gap between the actual poles of the slots. Ideally, I think it'd be better if these were slightly different shapes, but you've also got to make sure that these slots are thick enough where it essentially isn't going to twist, vibrate or bend in any way as it's being cut. So I did try to play it quite safe. This, as you can see, is the full width of the casing, and the problem is with this is this measures, I believe, about 105mm across. And as you might remember, I got 300mm sheets of silicon steel, meaning that I can only really fit 4 of these onto one sheet at a time. I ideally want to get a 10mm wide stator. These are 0.5mm each, so I need about 20 stators. This does mean with the amount of sheets that I bought, I wouldn't get enough pieces if I made any mistakes at all. It also meant that I wouldn't be able to cut this piece, which is the silicon steel stator, which I am actually yet to make. So to get around this issue, I decided I need to make this wall smaller and basically make the 3D print that you saw earlier the right shape to basically slot the stator into actual 3D printed casing. That then allowed the stator to be smaller with the rest of the actuator staying the same size, which it needed to be. Hence why I then modified the stator into this shape, so you can kind of see the bolt holes are cut off and it's just narrower here. You can then see how I've got all 9 lined up, all in a 300mm square. I did decide just to go with 18 sheets instead of 20, just so I saved on material if I made any mistakes. And so I made sure that I had enough material to make that rotor core in the future. So now we've gone over all that, we'll get it all assembled so you can see what it's like. In another video, I'll go over what I basically found trying to cut silicon steel on my pretty much hobby grade CNC. But overall, it went pretty well, even if it was a bit slow. After cutting all 18 out and then cleaning them up, which was quite laborious, I'll be honest, I then decided to clamp them in this little clamp that I made to make sure they're all centered together, ready for coating. These sheets weren't laminated, so I did just clear coat each piece before I clamped them together to make sure I covered that base. Then, to make sure none of the enamelled wire would rub through on the edges, I did find some gel coat in my garage, so I just decided to use that and brush some on. It wasn't very neat, but I thought it would suffice for this first go, and in the future I intend on getting somewhere I can just kind of dip it in and then pull it out. When it came to pressing all of this together in one of the 3D printed casings for this prototype, that is the point when I thought maybe I have made a mistake doing it this way, maybe I should have just ordered more material and done it through the bolt holes, because it was quite difficult to get it all to line up and press it in. As for the bearings, I went for these very standard, easily to get bearings, these being 24mm with 16mm internal and 5mm wide, with this big bearing being 52mm exterior and 40mm interior with this 7mm wide. It's worth noting that smaller and thinner ones do exist, but they only seem to be available from random suppliers over in China. Whereas these bearings, you can get Chinese ones, you can get Japanese, and you can get German, hence why I want to use these ones. And then you have these little bearings here. These are 8mm long, 8mm wide with an internal of 4mm. Now, you can get smaller bearings than this fairly easily, but you do have to go down in shaft size to 3mm. So I've kind of just got to stick with this because I don't want to go down that small. So it does mean the gears need to be 8mm wide and not 5. Again, you can get random bearings from China that are smaller, that are typically in actuators like Steadyway actuators, but I couldn't readily find them available at regular places. But as long as you account for that, I don't think that's a big deal. As you can see, these do fit pretty well into these 3D printed gears. I also got the wires fitted on and the terminals fitted onto the stator. This is the 3D printed rotor, and yes, it's not ideal that it's 3D printed, but it does show nicely how I've managed to get a combination where the magnets all fit in nicely and it all fits into the center. This is again using readily available magnets that are the easiest to buy. Also, yes, that is just a bolt super glued in for the shaft. And yes, that is literally just a bolt for the shaft for the rotor. That's for trial and error reasons. I am going to be making a new one shortly, but I'll explain why at the end. Then that's the back cover slotted on, and you can see the location for the Hall effect sensor. And in relation to the shaft, you might be able to guess why I need a trial and error for this. Now onto the planetary gearbox reduction. We've got the gears built up into the carrier that slot nicely into the ring gear. I do want to refine these gears in the future, but I think for these versions it's all right for now. You can at least see here that for a change it is all lining up nicely. And then lastly, to finish off, it's just put the front cover on with the bearing. With that slotted on, you can see it's pretty neat, apart from the fact that the gap where the stator sits. Those pieces are still pretty tight and I don't want to have to force them on to then struggle to get them off at the minute. Again, I think I've probably made a mistake by just not buying more material and then doing it the old way with the bolts. However, if we now compare it to actuators that I've featured in previous videos, you can at least see that this is quite thinner. It's also better for mounting the actual exoskeleton brackets on because the bearing sits out and the hub sits out way more. So overall, I'm quite happy with all of the dimensions of this now. It took some trial and error, but I can't see me being able to improve much, especially with the parameters that I've set with bearing sizes and things like that. So the question you might be asking at this point is, why doesn't it work, especially after I've made a silicon steel stator? The answer to that could kind of be a couple of things, but all culminating in the fact that The ESCs that I'm trying to use as basically a datum point to make sure I've got a working actuator before going into the motor controller sides aren't getting the correct back EMF signal to gain a position on what phase they're on inside the brushless motor. One of the problems with this is if you want to buy a decent brushless motor with forward and reverse, you end up buying one with a lot of settings like this one. And if you want a really basic one, you end up buying something like an aircraft one or a marine one that just does forward and reverse. But either way, there's a calibration point in both of these. So if they don't calibrate correctly with the correct signals inside when you turn them on, the motor won't work. I will say that with the Steadywin actuator that I did buy, that's now in pieces, I did actually try one of these ESCs on that before I took it apart. And it did physically work and move smoothly, but it did also work very slowly. It was only doing about 60 RPM, whereas when I had it working on the calibration software, it did far more than that. A way around this issue is using a censored ESC with a Hall effect sensor mounted on the back of the motor and a diametric magnet mounted on the shaft, which I'm having to include on this anyway due to the fact I want the position sensor for use with the exoskeleton. Now I want to make my own ESC motor controller anyway, so it's not too big of a deal. My only thing was I really wanted to get this working with a normal ESC just so I knew where I stood and knew I had a working actuator. Another thing that is probably at least not perfect is my actual stator design. I imagine there's improvements to be made there. The reason why I didn't try to make the perfect stator first is because I knew I would have problems physically making the thing out of whatever materials that I needed to use. So I knew I needed to try and make it within those parameters first. Just the fact that I haven't been able to get the silicon steel laser cut, for example, would have massively changed any design I might have preemptively made in CAD. The thing is, nowadays it's so easy to make something in CAD, but it's still not necessarily easy to make it in real life unless you can just 3D print it, which if you're using metals and stuff, that currently isn't easily accessible, at least on the kind of hobby level. Another issue is the fact that my rotor is still basically plastic with a magnet stuck around the sides, instead of those sheets of silicon steel making up the core with the magnets attached. So the future work on these actuators that will be in future videos is one, building a new rotor and with a correct shaft. Now, I did mention earlier that there was a reason why I just had a ball as the shaft, and that's because I need to work out and test Hall effect sensors on the motor. The reason I need to test it is there's a pricing difference when you try to buy these diametric magnets, which for anyone who doesn't know, imagine a donut magnet with the top of the donut being North Pole and the bottom of the donut being South Pole. That means that when you have a Hall effect sensor next to it, it can detect the position of a magnet depending on where the North and South Pole is on the magnet, hence put that on a shaft and you get your position sensor. But what I found trying to buy these diametric magnets is you can either buy these really small ones, which is what I've currently measured up for, which have like a 3mm interior diameter and about an 8mm exterior diameter. You can either buy those that are literally pence each to buy, or you have to go straight up to around 10mm and above, and these are immediately £10–20 each. It's mad the difference, and you're literally going from these minuscule magnets to quite big ones that also mean the designer has to change a little bit to accommodate it. So I need to test those little magnets with a Hall effect sensor, see if they actually work, see if they're sensitive enough, and then design the axle shaft with a keyway that goes through the rotor and then into the sun gear, and design it also all fits nicely on whichever magnet I choose to pick. I also want to remake this stator again because I'm just not really happy with how the current stator fits inside the 3D printed housing. I think I'm much better off accepting that I'm going to lose material and just cutting them out like this. They'll bolt together much easily. They actually came out better on the CNC. They just seem to kind of hold together and sit better on the board. I mean, this one I haven't even cleaned the swarf off it, try to hold it gently, and you can see it's pretty perfect. I really haven't had to clean it up or anything. And again, I haven't even wiped it off. However, before I make those new ones now, I do have the parameters of what I need to machine them, how I'm going to machine them, all of the things I've covered. I do want to use some actual like EMF simulation software to simulate the magnetic fields and make sure it's actually all going to work correctly. I have used some minor software so far, but really just to work out the best combination of slots and magnets, which is also why I'm on 27 slots to 36 magnets. This partially being dictated by the types of magnets and sizes of magnets I can get, as well as the thickness and length of slots that I need on the stator. Also, I'm going to do another video going into the silicon steel stators, but also the SMC stators, as I don't think many people are doing it, and it is actually quite an interesting thing. And if I can get them to work in the future, it is something you can do with basically just a 3D printer. And it was surprisingly easy to get good at as well. But the next video is probably going to be reworking the gearbox side of this. So originally when I started this, I got the gears laser cut out of steel, which is in this prototype here. It worked fairly well, but the problem is with the laser cut, which I've mentioned in previous videos, is it can warp the steel a little bit on certain parts of it, like where it stops or starts. Now it's very little, but if it's doing it on one tooth and then it basically warps that tooth by 0.2 of a millimeter, it does actually create a notch on the gearbox, so it's not ideal in that respect. The other issue is, as mentioned, I want to try and get away from actually involving third parties. The steel gears also do create quite a lot of weight, and because I've got to do them 8mm thick, as mentioned, that doesn't help that issue either. So what I want to try and do on the next video for this with the planetary gears is to make the gears out of plastic and carbon fibre. This is something I've experimented with the past with certain parts on the exoskeleton. Parts that I needed extremely strong, so I basically used either polycarbonate or even acrylic. Machined it however I needed it, and then did the same in carbon fibre, and then bonded carbon fibre onto the top and bottom of that sheet, and it created an incredibly strong material. So I actually want to try and make the gears out of that material. So using a hard plastic like acrylic that's 5mm wide as the centre of the gear, and then using carbon fibre back to each side of it to provide strength on the actual gear teeth. That way you've got a really hard, smooth running edge, but you've got the strength of the carbon fibre. If I can do that, not only is it lighter, but both of these materials are incredibly easy to CNC machine on just a hobby grade CNC machine. I was actually impressed with how well carbon fibre comes out as long as you keep that horrific dust down. So if I can do that, especially with the fact that I know my CNC machine is pretty damn accurate, then I'll have a much better gearbox and I can be much better and more accurate with the teeth and get better backlash. And then at the same time, I'm gonna have to start developing my own ESC/motor controller. I'll be most likely using Arduino. I'm not sure how difficult it's gonna be. I think with the use of AI, it won't be too hard. The main thing for me is I haven't actually designed PCBs in Fusion 360 yet, so I need to go learn that first to then design these. But with that being said, I hope you enjoyed the video. I hope it all came across correctly and made a degree of sense. There'll be more updates on the channel very soon, along with some other projects that I've been trying to work on in the background. So please feel free to like and subscribe, and I hope to see you on the next video.